triglycerides. We have fats and we have oils. These are very straightforward definitions of triglycerides. Fats tend to be solids at room temperature, and they not always, but tend to come from animal sources. So think animal fat, and they tend to be solids at room temperature. Consequently, because they have really high melting points, they tend to be nothing but saturated fatty acids. So these are important details. Oils, however, think oil liquid. They tend to be liquids at room temperature. Consequently, they tend to be highly unsaturated. And we tend to get these oils from either plants or fishes. Consequently, that's why they tend to be kind of smelly, because they have really low melting points. So make sure you memorize. Triglycerides have this overall form where they have 3 fatty acids, hence the term tri. 3 fatty acids that are attached to a glycerol molecule. Hence, we have the term glycer for glycerol and ides, with the idea that it now has 3 fatty acids that are attached in ester form. Let's go straight to a general example. So here is my line angle structure of a glycerol, and basically you can think of it as a compound with 3 alcohol groups attached to it. From an organic perspective, this is 1, 2, 3 trihydroxypropane. The biochemistry term for this, however, is glycerol. And basically what we have is we have a glycerol, we have a fatty acid, and I'm just going to draw any fatty acid for right now. Oops, forgot my oxygen. So we have 3 fatty acids, and basically it was a enzyme catalyzed esterification that occurred. We've now constructed three esters. I know it's getting kind of messy, but you can see those 3 esters, and this now is what we call a triglyceride. Now, the body loves fatty acids because it can break it down for long-term energy, and it has other purposes. But oftentimes when we like to store it, just as we like to store monosaccharides in the form of starch, that we often like to store fatty acids in the form of triglycerides. So let me say that again. When we like to store fatty acids, oftentimes we like to store them in the form of triglycerides. The triglyceride form can also be modified slightly to create a variety of other different types of, you can think of them as triglyceride derivatives. And we'll get into those in a bit. But this is the general form right here. A glycerol and 3 fatty acids esterified, forming what's called a triglyceride. So notice the 3 esters that are present. So I've beat that to death. Here's a nice, pretty example of a esterification forming a triglyceride. You'll be responsible for predicting this triglyceride if I go ahead and I give you these starting biomolecules. So make sure to know how to do this reaction. This reaction is very straightforward. It's a simple esterification. So in this case, the hydroxyl group from the fatty acid and the hydrogen from the alcohol are going to go ahead and form 3 waters. Consequently, the remaining portion of the molecules are going to form 3 brand new, and I'll erase those other marks, are going to form 3 brand new esters, resulting in the triglyceride. Now, as far as the name goes, you're not responsible for naming the overall triglyceride. No. I will expect you to memorize, however, the starting molecules, such as this being glycerol and these being the starting molecule names. So, for example, if I say stearic acid, I'll want you to draw a stearic acid molecule. I drew it in condensed form. Actually, I drew it in almost its molecular formula, just because this is a really small slide and I want to conserve space. Usually, I'll want you to go ahead on a piece of paper and actually sketch out the fatty acid. So in this case, stearic acid has 18 carbons, so 2, 4, 6, 8, 10, 12, 14, 16, 18. Let me go this real quick. 2, 4, 6, 8, 10, 12, 14, 16, 18. So I want you to go ahead and actually sketch it out. You're responsible for this chemical reaction. Let's go ahead and move on. Hydrolysis. Again, we've covered this type of reaction in the previous slides when it comes to esterification. So in this case, we use water to go ahead and cut apart a triglyceride. So let's say we want to break down a triglyceride so that we can use the fatty acids for energy. In this case, we would need 3 water molecules, and I'm going to go ahead and actually draw out the water molecules just to show this. You would need 3 water molecules in this reaction. In the past, we've used acid as a catalyst to break it down, and if this were a saponification reaction, we would use a base. When it comes to biochemical hydrolysis in the body, it's very pH sensitive. So what they use are enzymes to catalyze the reactions. So they use nearby solvent molecules as well as the enzymes. In this case, the name of the enzyme is a lipase. And with our 3 water molecules, the hydrogen is going to go ahead, and I'll go ahead and I'll use my yellow pen. The hydrogen is going to go ahead and combine with the glycerol component, forming glycerol. The leftover hydroxides are going to go ahead and combine with the remaining carbonyl groups, forming the brand new fatty acids. So you're responsible, if I give you the reactants, to go ahead and predict the products. If I give you this type of reaction and you sketch the fatty acids, I may also ask you to name them. So make sure you can sketch and name the fatty acids. Let's go ahead and move on. Here is a classic saponification reaction. This is a commercial reaction. Why? Because cells are pH sensitive. You're not going to find a strong base floating around inside a cell. So this is the commercial way of creating soap. This is completely redundant. We've already talked about this reaction in two different parts of our previous organic chapters. But again, I could still test you on it since this is a since we're now looking at biomolecules. So I could give you a triglyceride here. I can give you a strong base. Notice we have 3 sodium hydroxide molecules. And you should be able to predict what's going to happen. In this case, the sodium is going to go ahead and combine with the carboxyl group over here. And it's going to form the 3 what we call acid salts. The acid salts, notice they have these really strong ionic forces at the head, which makes them really polar. Consequently, you have the nonpolar tails, so these are classic soaps, hence the term saponification. Now, the remaining portion of the hydroxides are going to go ahead and fit on the this portion of the molecule, which is going to go ahead and form glycerol. So you're responsible for this reaction as well. This is a brand new reaction called hydrogenation. Please take a look at the name. See where it says hydrogen in the hydrogenation portion of the name? What do you think we're going to be adding in? Hydrogens. So this is this example is a commercial example because it requires nickel as a catalyst. We actually do have hydrogenation reaction in a cell, although that would require a biochemical catalyst such as an enzyme. But in this example, I'm only going to test you with the industrial version. Hence, I'll give you a metal catalyst such as nickel. But this helps speed up the reaction. But notice here, hydrogenation. So if I give you the hydrogens, this is a reduction reaction. And basically what we're going to do is we're going to add in 2 hydrogens onto a double bond. Consequently, here is before and here is after. Notice the double bond is gone. So I'm going to write that there because that's poetry. The double bond is gone. So in this case, I added in 2 moles of H2, and I went ahead and I removed the double bond. So technically, there were 2 double bonds here. That's where you have, and I'll highlight this using my highlighter. Technically, there were 2 double bonds here. Again, we were short on space, so we drew it in the condensed form. I don't want it in the condensed form. I want it in the expanded form, and I'll usually give you those examples in expanded form. But in this case, there were 2 double bonds, which is why we have 2 moles of this. So if I give you, and I'll just highlight it here. If I give you this portion right here, you should be able to go ahead and predict the product, showing at least the removal of the double bonds.